Hello girls, welcome to this lesson on the rules of differentiation. So in yesterday's lesson, the live lesson, we looked at gradient from first principles, and the first principles formula is kind of the proper mathematical way to work out the gradient anywhere on a curve. And like I said yesterday in the lesson, you will be expected in a test or exam to do at least one question that is using first principles, but there is a shortcut. And that's what we're going to look at in this lesson. So what I'd like you to do is to look at the table that you see in front of you. And in the left column, we have a function, different functions. And in the right column, we have the derivative of that function. Remember, the derivative is the gradient of that function at any particular point. Okay, so these gradients in the right-hand column, we could have got those by doing first principles for any of the seconds. So I'm going to just show you quickly. Let's take x cubed as an example, and I'll show you through first principles how we get 3x squared. Right, so I've just showed you with this example how we find out the derivative of x cubed to be 3x squared, which is confirmed in the table here. So what I'd like you to do is to pause the video and look if there's a relationship, if you can see a relationship between each function and its derivative. There is a kind of a formula that I want you to look at and see if you can understand what that is before I carry on. So pause the video now, spend a minute or so looking at that, and then unpause. Alright, so what I was hoping that you would have seen is that in each case, to get the derivative, instead of using this whole complicated first principles formula, there's a very quick shortcut, and that is so look at the x squared in the f of x column. So if we take that exponent 2 and we multiply it to the coefficient, which is 1, and subtract 1 from the exponent, we end up with 2x. Okay, let's try it with x to the 4. So multiply the 4 to the coefficient, which is 1, so 4 times 1 is 4. There's the 4, and subtract 1 from the exponent, so 4 minus 1 becomes 3. Check it with x to the 6. Multiply 6 to the coefficient of x, which is 1, so 6 times 1 is 6, there's the 6, and subtract 1 from the exponent, which gives us 5. Okay, and then you can also see it here in variable terms, where the coefficient is k, the exponent is n, and we have n times k, which gives us the new value of the coefficient, and then subtract 1 from the exponent, n minus 1. Alright, so that is a shortcut. So if you have a look at all your previous examples and the previous exercise that you did, you can apply that shortcut to all of those in order to work out the gradient or the derivative or the instantaneous rate of change, whatever they're asking for. Alright, so 3 basic rules we're going to look at. Firstly, rule 1 says that if f of x is given as k, that k is the coefficient, times x to the power of n, then the derivative of f, or f prime x, is equal to kn x to the n minus 1. So they've taken the exponent n, multiplied it to the coefficient k, and subtracted 1 from the original exponent. Rule 2, if f of x is equal to kx, then the derivative of f is equal to k. Right, essentially what this means is this is a linear function. Right, it's not x squared, it's not x cubed, so it's a straight line, which means that the gradient is whatever the coefficient of x is. And as you know, if I gave you a graph y equals 3x, you know that the gradient is 3, wherever you are on the graph. There's no variable in this case because the gradient is constant throughout the curve. Alright, so if you wanted to have a look at it in terms of the rules that I've taught you, the exponent of k to the x, let's have a look. So if I said f of x equals k to the x, k times x, the exponent of x at the moment is 1. So if we then apply the rule that I've just taught you, then the derivative of x will be 1 times k, which is k, and then 1 minus 1 for the exponent, which will give us 0. So x to the 0 is 1, which gives us then a derivative of k. Okay, third and final rule. If f of x equals k, in other words, constant, then the derivative is 0. Okay, so just try and put some perspective to this. If f of x equals a constant, that means y equals a constant, which means this graph would be a horizontal line through the y-axis. So obviously a horizontal line has zero gradient. So the short rule is that the derivative of any constant is always zero. Okay, at this point, I'd just like to show you these 6 definitions linked to your exponents, where we need to be able to manipulate expressions before we can differentiate them using this short rule that I've just taught you. Okay, so let's look at them all individually. So for A, the whole idea here is that we can, and in all of these examples, we're differentiating x. All right, so the idea is that we can remove x to the n to the right of the fraction. And the reason we want to do that is because now 1 over a is the coefficient. All right, B, the same thing. We want that x to the n to be on the right-hand side of the coefficient. So if we bring it up to the top of the fraction, it becomes x to the negative n. Okay, now the coefficient is a. Right, if we look at C, again, only the x to the n comes to the right of the fraction, and we change the sign of the exponent, and a over b is now the coefficient. For D, the whole b to the x is raised to the power of n. So we would bring that whole b to the x out of the bracket and make it b to the x to the negative n. Okay, alternatively in this case, you could say, and I'm going to just draw it here, you could say that a is over b to the n x to the n, which would also equal a over bn, and take the x to the top. Okay, so that's also a way that you can do it if we're differentiating with respect to x. All right, then we look at E. This is using your surd law. Okay, so when you have an x in a surd, we need to get rid of that surd before we can use these rules. So the rule is we take the base, which is inside the surd, which is x, and we take its exponent m divided by the outside n. All right, and because it's in the denominator, we've got to then make that negative. So it comes to the top and becomes minus m over n. All right, and then F, similar thing happening here, but now we don't have a denominator. So we're going to take just the x to the m out. The a we can leave inside the surd because we're not differentiating the a. So the x to the m goes out and it becomes x to the m over n. All right, let's do an example or two, and that will be the end of this lesson. All right, before we continue with the examples, I just want to do a little bit of notation with you. So we've already said that f dash x or f prime x represents the gradient of a function. Obviously, we can use g dash x when we're talking about function g, but also if you are given a function y equals something, then we can say that the derivative is dy over dx. Okay, so that means the derivative of y with respect to x. All right, another way that we can show it is dx shows the derivative. A fifth way we can show it is y prime. And in the next few examples, I'm going to be showing you all of these. Right, example 1a, determine the derivative of f if f of x equals 3x to the 7 minus 5x plus 2 root x plus 7. Firstly, what I'd like to do here is to rewrite it in a form where we can differentiate. And what I mean by that is that there shouldn't be any variables in denominators, and there also shouldn't be any surd signs. So the 3x to the 7 is fine, the minus 5x is fine, but we need to change the root x to 2x to the power of a half plus 7. All right, now we're ready to differentiate. So we show that we are working with the derivative of x, and we now apply those short rules. So we take the exponent 7 times 3 gives us 21, and subtract 1 from the exponent gives us 6. Then for the next one, and you might remember your rules, we can go straight to minus 5, but if you can't remember that the exponent here is 1. So 1 times minus 5 gives us negative 5. And then if we subtract 1 from this exponent, we get x to the 0, which is 1. Right, for the third term, we're going to take the exponent of half times 2, which is 1, and subtract 1 from the exponent, so a half minus 1 is negative a half, and the plus 7, remember the derivative of any constant is 0, as I explained to you in the rules. Okay, sometimes I do ask you to leave your answers with positive exponents, so we would need to rewrite this as 21x to the 6 minus 5 plus 1 over x to the half. It's not necessary to put that x to the half back in surd form. You can leave your answer as that. Okay, example 1b. Determine dy over dx. That's another way of just saying determine the derivative. If y equals mx minus 3m all squared, where m is a constant. Alright, so the first step that we need to do here is to multiply out that bracket. Alright, so if we multiply out the bracket, we get y is equal to mx squared will be m squared x squared. The outers will be minus 3m squared x. The inners will be minus 3m squared x, so that's minus 6m squared x. And the last will be plus 9m squared. Right, now they've told us that m is a constant. So in order to work out the derivative, we're going to now say dy over dx. That replaces the y. And we take, again, the coefficient, the exponent of x, which is 2, and we multiply to the coefficient of x, which is m squared. All right, because m is a constant. So it's going to be 2 times m squared, which is 2m squared. And then we subtract 1 from the exponent, which is going to just then be x to the power of 1. Okay, now in the second term, again, the exponent of the x is 1. We multiply to the coefficient, which is minus 6m squared. So then our new coefficient will be minus 6m squared. And x to the 1, we subtract 1 from its exponent, which becomes x to the 0, which is just 1. Okay, then the 9m squared is a constant on its own, so its derivative is 0. Remember, the derivative of any constant is 0. So that is our final answer. That's our derivative. All right, I think that's enough work for this lesson, girls. It's only a single. So please, if you do have time, go over the examples again, and we will move on with more of these examples in tomorrow's lesson as we continue with rules of differentiation. So there's no homework, but I would like if you go over the work just to make sure that you fully understand what I've said. Please send me a message if you have any questions or you want clarification on anything.